pretty new to Lightning Network development, but joined the core Lightning team there, and I'm going to present on Minisketch and what I've learned about the Gossip Network. So I've titled my talk Magical Minisketch and the Lightning Gossip Network. So I'm going to go over kind of the role of Gossip in the Lightning Network. Is everyone kind of familiar with Lightning, or at least semi-enthusiasts? Okay, so I'm not going to spend too much time on the background of how Lightning works, but I will explain how Gossip ties into it. So I'll try to give at least a high-level overview of how Minisketch works, go through an example, and then explain how we can use this to improve Lightning Gossip. So the role of Gossip in the Lightning Network, I thought it might be kind of fun to explain this through example. So we're just going to dive into like a basic Lightning transaction. So for like an average user, I figured it's probably something like you pull out your mobile app, you're presented with like a QR code for an invoice, so you scan that, and then on your app it gives you the memo with the notes, kind of verify that the amount looks roughly correct, and you hit send, and then with any luck, a moment later you get your little green checkbox showing that it was successful. But being as how we're enthusiasts here, I think we should go a level deeper and see what was kind of going on behind the scenes. So in core Lightning, at least, there's a lot of CLI commands we can use to get some more information. So in this case, we can see that yeah, it indeed went through. It was complete. We got our pre-image. That's kind of like our receipt of payment in the Lightning Network. But really interesting is like down here, we see that this was actually split into 12 different parts. So that's like 12 different routes that were calculated and all filled in order to fulfill that invoice. So this is fun. Let's go one layer deeper, and we can actually see that it wasn't just 12 routes that were attempted. There were actually 53 different payment attempts as part of a multi-part payment. Some of those timed out. We actually got some errors before it was successful. So this particular CLI command, it prints out pages of data, but we can actually tell on each failure where along how many hops deep that was, and we get this hex encoded string here, and if we feed that into another tool we've got, we can actually decode this. And so this is part of bolt 4. It specifies that 1007, that meant we had a temporary channel failure, and we actually included in there a channel update. So there's a complete channel update packet. And so this was kind of like that intermediate node. It doesn't know who we are because everything's onion routed. It doesn't know where we were trying to get, but it's saying whatever you're doing, I think you're barking up the wrong tree here, because there's you obviously have some outdated information, and I think you need to see this. So in this particular case, we can see we've got some information on what sort of fees this particular channel charges, what the CLTV delta is, how many blocks we need to add for that timeout. But really the important part is right here, channel flags equals 1. That doesn't really sound like much here, but this is actually a flag. If we look it up in the protocol, it says this channel is disabled. So obviously, when we were calculating the route, we didn't have that information, and that was why this particular one failed. So basic example, but what have we learned? There were actually over 70 different channels that we utilized to make this payment, even on a fairly simple scenario. Some of them we had outdated information, but we were able to retrieve some new gossip there, update our graph, the routing graph, which is kind of like our map of what the network looks like. And with that new information, we were able to calculate, recalculate our paths such that we were able to ultimately succeed and make the payment. So just kind of backing up and starting from a high level now, what's generally the role of gossip in the network? Well, it's kind of just like in real life. Gossip is secondhand information that you share about peers whom you're not directly communicating with, right? So in the Lightning Network, we've got all these different nodes that are connected. We might have direct connections to a handful of them, but if we're down here in that lower left corner, we need to collect information on all the different nodes that are out there. So we do this in the form of a gossip message called the node announcement. This one gives the public key of every node, and it also gives addresses for like how to reach them if we wanted to connect to them directly. So that's like your IP address or your onion address, like WebSocket, like anything you want to dream up, like you can actually include that and in the node announcement. So the next thing we need to know is where the channels are. So we've got a channel announcement type. This basically, all it really does is it says between node A and node B, there exists a channel. And it was funded with a transaction on the blockchain. So it lists the short channel ID, which is like everything you need to look it up and see which UTXO on the blockchain funded it. That part in particular is not like great for privacy, but it's really good to prevent like denial of service. Like you have to prove that you have a UTXO to open a channel. So now we have kind of like the basic topography of the network if we wanted to route across it, but it helps to have a little bit more information. So we get this in the form of the channel update. Again, this is stuff like the feeds, or if a channel has like the max HTLC size set too low, or is otherwise maybe disabled, like we saw in those examples. Like those are the things that we would want to just kind of eliminate that from our choices when we go to calculate a route. No, that's not good.
That's projected.
Yeah, that's a projected. So I guess the gist of that is that now we have everything we need to be able to construct our route. So like just a few details about the gossip network.
Shut down before you turn it back on. Yeah, it has to go through a power down cycle before you can turn it back on. So it might be a minute.
I'll talk about it. I don't have I got through like some of the more fun visuals. So why did I call this talk the Lightning Gossip Network? Like, are we just talking about the Lightning Network? The short answer is like not really. It's a little bit different in that we see all the connections we have with channels between nodes on the Lightning Network. But when we talk about gossip, we're actually only communicating with like a subset of those. So depending on the implementation, like Core Lightning, I think uses 5 peers, but it's anywhere between 3 and 5 that you're connected with, that you're gossiping. Oh yeah, you are disconnected. And so, yeah, actually, it doesn't even have to be one of your peers that you're gossiping with. You can gossip with like any nodes, and it really doesn't even have to be a node. So long as there's a machine out there that knows the protocol and is providing you like new information that you didn't have from your other peers about gossip, like we're totally happy just communicating back and forth with you and gathering new information on the state of the network. And then kind of the last important detail about it is it operates with flood propagation. So that's like, say you're connected to 5 peers, you'd receive information from one peer, and you just kind of naively rebroadcast that. If it's good, new information, you just rebroadcast that to like 4 other peers. This is really efficient early on in the propagation because you quickly fan out the information to all the peers. But even after like several hops, it starts to kind of lose efficacy. Like all of a sudden you're starting to get, from multiple sources, you're seeing the same data and you're kind of just losing efficiency. I'm going to try to reconnect, but it might take a minute. You want me to do it while you keep talking? Sure. Well, I might do that to see where I'm. Yeah. Go. Okay, so just some basic statistics on the state of the Lightning Network. Right now, we've got some 80,000 different channels and 17,000 different public nodes. So going back to that flood propagation, if we're looking at the bare minimum of like 3 connected gossiping peers, that means that in order to fan out and reach the entire network, we're looking at like a minimum of 14 hops. And the way that this works is there's kind of like a rate limiting built in to gossip propagation. So you actually batch all the new gossip that you receive, and you wait 60 seconds to 90 seconds. Core Lightning uses 60 seconds, but I think LND maybe uses like a 90-second cycle. And you periodically broadcast all of the new gossip you received in that time to your gossip peers. So that means that we're looking at 14 hops, 60 to 90 seconds between each one. It takes a while to fully propagate to the whole network. And yeah, in practice, we're seeing something like 95% of the network receives it within about 13 minutes. Really, you need like probably 20 minutes. That's a good rule of thumb at minimum before you can count on everyone seeing your new information. Okay, so switching gears, I'm going to try to explain Minisketch. I'll do my best here. It's a set reconciliation protocol. And so what set reconciliation is we basically just got 2 data sets. We can see in this Venn diagram that they are largely overlapping. And so in this case, they both have valid data. And we want to make sure that we get the sum of that data and make sure that both of them are updated with it. So in this case, we're interested in the symmetric difference between the sets. And that's what Minisketch helps us do. So if you're kind of like I was a few months ago, you might sort of think that this is kind of a hard problem to solve. You're going to have to there's going to be some overhead in trying to reconcile these 2 sets. You're going to send more information than is strictly required because you don't know what your peer doesn't have. But like me, you would be wrong because Minisketch has some really cool properties. So it actually comes from a family of error correction codes called Bch Error Correction. It uses some nice math, like the Berlekamp-Massey algorithm, which we'll get into later. And I'm just going to try to go through like a really brief, high-level example. Hopefully I'm getting this right. So imagine we have 2 sets of data. They contain the elements 1, 2, and 3, and 1, 2, 3, and 4. So kind of like a cool trick we can do if we want to reconcile these sets and make sure both of them have all the data, is we take the sum of the elements. So here we've got 6 and 10, and we want to transmit, say we're on the left side, we want to transmit to this data set on the right, like, okay, here's my sum, it's 6. We can take the difference, 10 minus 6, and we arrive at 4, which is our missing element. So, okay, cool property, but we're basically just doing subtraction here, right? Yeah, so this basically only works with exactly 1 element anymore, and there's obviously no way we can do anything. But we can actually do another trick where, say we want to encode 2 differences, we can actually take the simple sum of the elements in this array. So here's our array. The first element is the sum of the elements, and the next element of our array is the sum of the squares. So I've gone ahead and done this basic math. So now this is the data in this array that we're going to transmit to the other guy. It's twice as much to reconcile like 2 differences now. But basically, we can take the difference here, and we say, okay, so that difference is the sum of the elements, and this one's the sum of the squares. So thinking back to algebra, we've got 2 equations, 2 unknowns. That means it's solvable. And luckily, as this order gets harder, this becomes a really difficult problem. But that's where the Berlekamp-Massey algorithm comes in. It's a really efficient way to solve this. And we can use this for like an arbitrarily large set size. So we can, go all the way up to order n. And obviously, it takes a little longer the higher this order goes, because you have to encode every entry that you add up to the nth order. But it does work, and we can resolve a large number of differences with it. So Minisketch is a C++ library that was developed by Peter Willa, and it's implementing the pin-sketch algorithm. It runs on like a wide range of architectures and hardware, and there's also it's optimized with like some tables to help solve the roots in a time-efficient manner. But he's also got a pure Python implementation, which is really impressive in itself. It can do all the calculations in it's like 500 lines of code, which kind of blows my mind. So if anyone's interested in it, it's pretty accessible. I'd encourage you to check out his GitHub page, c+/Minisketch. All right, but supposing you're just an engineer like me, and it's like, okay, how do we use this, fancy math in practice? So it looks something like this. First, we initialize a sketch, and in order to do that, we need to know what's the width of the data that we want to encode. So in this case, we're talking like it's 64 bits wide. So we give it 64 bits, and then we need to tell it the capacity. So this is like how many differences do we want to be able to reconcile between the two sets. If we think that we're going to have about 5 differences between them, we might choose something like 8 just to make sure we're covered, but we don't want to get too carried away. So then we add our data and calculate the syndromes, which that's just like each line of this. We have to calculate it as we add each data point. So then we serialize and transmit that over from Alice to Bob. Bob goes through the exact same procedure. He builds his sketch, and he merges the two together. And it's pretty interesting. He actually doesn't have to choose. He needs to choose the same data width, but his capacity can actually be different. And the way that the math works out is you can actually just kind of truncate this array at any point so that they're equal, and then you can merge those two sketches. So you lose some of your capacity there, but they merge and are able to be solved just fine. So yeah, then you use that. We're looking at Massey algorithm that solves it, and the result is all the data that you're missing between the two. Okay, so kind of what properties does this have as we use it? It can support anywhere from 2 to 64-bit wide data. And the really cool thing is that the serialized size that you're transmitting between the peers is actually the sketch capacity. That's the number of entities that you want to resolve times the data width. So if you choose that sketch capacity just right, it's like 100% efficient in how much data you can get out of it, which that part just really blew my mind. And then some other things to keep in mind. As you increase sketch capacity, the reconciliation time scales up, and depending on the number of differences that you actually have to resolve, that kind of scales like quadratically. So you want to keep the differences kind of bounded. You don't want to get too carried away with how big the set differences are there. And then just like a couple basic considerations to keep in mind. You can encode an element of 0. When we initialized our sketch, it was kind of with null elements. So you can choose any number apart from 0. And then the other thing is, it's also generally helpful to make sure that the number of elements that are in each sketch, that they're not so different that they exceed the sketch capacity. Like normally this isn't a problem, but if you imagine you have like 50 entries in one sketch and 100 entries in the other, and your sketch capacity is only 10, like there's no way it's ever going to solve because the capacity is just not there. The cool thing is it kind of gives you a warning if it can't solve it. It just says, look, I can't find any polynomial that actually satisfies this equation. And that works like most of the time. All right, so just some background on how we're going to use this. It's actually, Bitcoin ran into a fairly similar problem that Lightning Network Gossip was facing when they were, faced with the issue of the transaction relay also not scaling very well with flood propagation. And so if you're familiar with the Relay protocol, that's what Minisketch was actually developed for. And Relay uses this to encode each transaction that's in the mempool. You want to share that with peer Bitcoin nodes. And so those are a 32-byte transaction ID. Obviously, we're limited to only 8 bytes with Minisketch. So we need to compress that down to a smaller fingerprint that we know which transaction we're talking about. So yeah, there's a hash function to do that. But yeah, they reconcile inventory sets in order to do that. So that's another element that complicates it a little bit. But instead of, so say we have the whole mempool, one way you could do it is encode every single transaction in there into a sketch. Both peers do that, and they resolve it, and they see what differences they have. That's not actually how Relay works. What Relay does is it keeps track of each peer that it's communicating with, and it says, hey, it's been 15 seconds since we last talked. I'm keeping an inventory of everything that I wanted to tell you about, but I haven't yet. So here's 5 items that I've been meaning to tell you about. Meanwhile, your peer, Bob over there, he's kind of doing the same, but maybe he collected 7 items, right? And so then instead of encoding, all however many thousand items in the mempool, it's really just the 5 items and the 7 items. We reconcile those, and maybe we find that there's only 3 differences between the two. So once those are reconciled, those inventory sets are zeroed out, and they're ready for the next round that's going to take place, in another 15 seconds. So there's, yeah, the problem that Bitcoin faced with transaction relay was pretty similar. Yeah.
No, sorry.
Oh, okay. It was pretty similar, but there's a few differences. So for one, anytime you introduce that short hash function that produces only a 64-bit fingerprint, now all of a sudden we have to be concerned with collisions between the hash functions, and someone could potentially take advantage of that and kind of grind out a hash that would resolve, to the same fingerprint, and that would be a denial of service vector. So yeah, there's some concerns like that. Also, timing analysis, because transactions are supposed to be private. We don't have to deal with really either of those things with Gossip because it's public by nature, and also we can, instead of having to use that hash function, we have a trick for that, which I'll get to in just a moment. Also, we don't just have a single data type. We have 3 different messages that we want to relay. So those messages are the channel update, the node announcement, and the channel announcement. So of these, the channel update, again, that's your fees, whether the channel is active or disabled, what the maximum HTLC it can support, that sort of thing. That's 97% of the network traffic. So that's the big one that we want to make more efficient. But also, these top 2, they are only valid for a 2-week period. So these are repeatedly broadcast. Okay, so our challenge is we encode all 3 of these message types. We can only use 8 bytes. But we have kind of a tool in the form of the short channel ID. Again, that's what links a channel to the funding transaction on the blockchain. So by its nature, there can only be one unique transaction on the blockchain. So that's kind of a cool shortcut we can use. Also, let's see, on this node announcement, this doesn't have any channels linked to it, so it's kind of hard to use the short channel ID here. Ideally, we'd like to refer to the node ID. That's like the public key of the node. But unfortunately, that's 32 bytes. So again, we have to like hash it or something. But what we can actually do is when we encode this, we can use these elements here. This basically is the short channel ID. We can actually refer to a node announcement by just saying like, hey, here's the node's oldest channel, and we just point to which side of the channel that node's on, and that way we have a way to canonically identify which node we're talking about. So anyways, this is normally like 8 bytes of data, and we're trying to fit the whole thing in 8 bytes. So basically what we've done is shaved off a few bits that we don't really need. I'm assuming like if we can get 32,000 transactions into a block, that's probably sufficient. And if you're funding a Lightning channel, you're probably not going to have more than like 1,000 outputs. So we saved a few bytes here. Now we have room that we can leave a couple bits for which message type we're talking about, and then like which side of the channel that's on. So this is the way that we can identify in just 64 bits exactly what the gossip messages we're talking about. So finally down here, we've got the timestamp. For those periodic messages, we need to know which one's the new one, which one's the old one. So having some bits down there to differentiate those is helpful. So what does this buy us? Well, like the short answer is we can save at least 60% on bandwidth consumption for spreading gossip. Now that we've done this, we can actually communicate with more peers. And communicating with more peers is really great because that increases the reliability of gossip propagation. In particular, node announcements have kind of suffered in the past because the other two types, you kind of have some simple heuristics to figure out if you're like probably missing one of them. For a channel update, we saw in that example in the beginning, like worst case scenario is we fail a route, and then in that error packet we get an update anyway. So like we can kind of get some of the other data types back, but node announcement, that tells you like the IP address of the peer to connect to. Like if they change that and you never see it, like you might not just be able to connect to your peer. So that one's really catastrophic and should really benefit from the increased reliability. So still have a couple outstanding issues to decide upon. One of these is we can keep either global sketches or we can do the per peer sketches with like inventory sets. There's arguments for both. Another thing is that we also have rate limits for when we accept gossip. And if we're rate limiting gossip pretty aggressively, actually this like really cuts into our sketch capacity. So it would be nice for the implementations that opt into this like set reconciliation if everyone can kind of agree on like a common criteria for when to like rate limit. And I'm barking up like the block height tree, and I'm trying to get everyone on board for like if we can just link each gossip message to a certain like the current block height. Let's just say like you get one message per block height or for every 100 blocks or something. And that's like really easy for anyone to validate since you're already running the full node anyway. And then finally, in the future, we'd really like to get away from the short channel ID in gossip because it does leak privacy. You don't really want to dox all your on-chain UTXOs. We're not quite ready for that just yet, but when we do, it's going to lead to this like per peer inventory set solution. So that'll probably inform this decision. Okay, so yeah, gossip is what lets us build our like graph view of the entire Lightning Network and find a route. And Minisketch is really cool. Everyone should check it out. And hopefully we'll be able to use it to improve the reliability of Lightning Network gossip. So here's my contact info if you want to follow my work. It's you can see some of it on the Lightning Dev mailing list. I'm endothermic dev on GitHub and Twitter. So yeah, feel free to reach out.
How are we doing on time? Okay.